Today we're starting section 6.3. This is page 397. Check your understanding. And before we get started, section 6.3 is on binomial and geometric random variables. And binomial and geometric random variables will now follow binomial and geometric distributions. So think about the distributions we've talked about so far. We have the normal distribution, we've talked about the distribution of random variables, and now these are certain types of random variables we can have the distribution of. So when we're always looking for the conditions, these will have their own conditions with them. So to introduce her class to binomial distributions, Mrs. Desai gives a 10-item multiple choice quiz. The catch is students must simply guess an answer, A through E, for each question. Mrs. Desai uses her computer's random number generator to produce the answer key so that each possible answer has an equal chance to be chosen. Patty is one of the students in this class. Let X equal the number of Patty's correct guesses. Now, the first thing when you're reading a question is you should try to figure out what sort of distribution it follows. And in fact, the first question here is going to go along with that. So it says to show that X is a binomial random variable. As you're reading that, you should start to think of what sort of distribution it follows and what the conditions are for each of the distributions. Now remember, for a normal distribution, we need to have a continuous distribution. You can tell here, since there are a countable number of events, this isn't continuous, it's more discrete. So then we're going to go through checking for binomial. Now remember, for binomial, you want to check to see if it fits. So we're going to go through the 4 conditions for fits. The first one is there is a fixed number of outcomes. In this case, n is equal to 10. So the F stands for fixed. Then the computer randomly assigned correct answers to the questions, so we know they are independent, is our next condition. The I in fits is for independent. Our third condition, there are 2 possible outcomes. Success is question answered correctly, and failure is question not answered correctly. So the T in fits stands for 2 possible outcomes. Now for success and failure, success is always what you want to occur, whether it's a good thing or a bad thing, and then failure is what you don't want to occur, again, whether it's a good thing or a bad thing. So don't think success has to actually be a positive thing. It's just what you are looking for. And then the probability of success, P equals 0.2, is the same for each trial. And that last condition is that the probability has to be the same. So to check to see if a random variable is binomial, if it follows a binomial distribution, you're going to check to see if it fits. There's a fixed number of outcomes. Each of the outcomes is independent from the others. There's 2 possible outcomes, and the probability for each is the same. So in this case, it is binomial. So we've satisfied that. We know that the n is equal to 10. So think about when we were working with normal, we would always define our distribution. And we would say, for instance, before it was normal with a mean of and a standard deviation of. Now for binomial, we're going to check to see what our n is and what our p is. Those are the 2 parameters for the binomial. So we have figured out that it follows a binomial distribution where n is equal to 10 and p is equal to 0.2. From that, we're going to go on to find find the probability that x is equal to 3 and explain what this result means. So since we know that this is binomial with n equals 10 and p equals to 0.2, we're going to use the formula for binomial distributions. Now that formula can be found in your resource packet. Remember, we're always just kind of working through this. So we've gone through our probabilities, our expected values, and the variance of the expected. Now we're here in binomials. This is the formula for a binomial. So probability that x is equal to k is n choose k, p to the k times 1 minus p to the n minus k. So we can write down that formula and work through that. In this case, it's probability that x is equal to 3 is equal to our n is 10, choose k is 3, and our probability is 0.2 to the k, which is 3, times 1 minus p, which would be 1 minus 0.2, so that's 0.8, to the n minus k. Our n was 10, our k was 3, so it's going to be to the 7th power. In our calculators, now I forgot to bring home my calculator, so I'm going to be doing it on the calculator on my phone. We can use this formula by going to math, probability, and then this NCR is the choosing. So our N was 10, choose 3. We get 120 times 0.2 to the 3rd power times 0.8 to the 7th power. And we find from that this is going to be equal to 0.2013. So there is a 20% chance that Patty will answer exactly 3 questions correctly. So we have our probability and we've put that into context. There is another way to do that in the calculator, just like we did with distributions before. So instead of using the formula like we just did, you can go to distributions, just like we did for normal distributions. And this time we would go to a binomial distribution. Because we're looking at exactly equal to, it's a PDF rather than a CDF. Remember, CDF stood for cumulative. PDF, I like to think of precise. So P as precise, so it's an equal. Cumulative is an inequality. So it would be PDF. We had 10 trials. Our N was 10. Our probability was 0.2. And our X is 3. And we're going to paste that in, and we get the same answer. So either way works. And then to get a passing score on the quiz, a student must guess correctly at least 6 times. Would you be surprised if Patty earned a passing score? Compute an appropriate probability to support your answer. So for this one, we're looking at inequality instead because it says at least 6 times. So we're going to say that we're looking at the probability that X is greater than or equal to 6. Now remember, if I'm going to use what we did up here, we need it exactly equal to. So we'd have to find the probability X is equal to 0, X is equal to 1, X is equal to 2, X is equal to 3, X is equal all the way up to 5, because this is equal to 1 minus the probability that X is less than or equal to 5. So we would have to find all of those. Or we could use the cumulative function. And again, to do that, I would do 1 minus, go to my distributions, go down to the binomial, and this one's going to be a cumulative density function. Our trials is still 10. Our probability is still 0.2, but now our X value is going to be 5, and we're going to paste that in. And that gives us our probability. 0.0064. So there is only a 0.0064 probability that a student would get 6 or more correct. So we would be quite surprised if Patty was able to pass. So remember, when we're doing a exact equality, we're going to use the PDF function, or we're going to use a formula that's given in the resource packet. If we're given an inequality, just like with the normal distribution that we worked with before, anytime it's a greater than, we're always going to do a 1 minus to turn it into a less than. But unlike the normal distribution, this is a discrete distribution. It's not continuous. So if I'm going to make it less than 6, that would mean it's going to be less than or equal to 5 because we're skipping from 5 all the way to 6 and there's no numbers in between. And then again here, you can still use the formula, but you would be doing probability x is equal to 1 plus the probability x equal to 2 plus 3 plus 4 plus 5. Take the sum of all of those and do 1 minus that. With your calculator, it's not as bad as it sounds, but it is still easier to use the binomial CDF.